you hear me?
How we can hear you?
But there's so many people in my meeting.
We are curious
No,
about your
I'm
presentation.
free now. I'm free now. I have nowhere to go.
I'm free too. I have nowhere to go.
We also interesting about for your note.
Yeah, I'm a bad presenter, you know. There's no satisfaction listening me present.
Yeah, I'm here to see how bad it is. Let's see.
How to do it? Alright, do you guys see this? True.
Yep. Yep.
Yeah,
can see the screen.
let me start presenting. And as Christopher know, sorry Christopher, Dr. Christopher. Last time I present about the mathematical variety, but in the process of trying to understand it, we venture into GIT, and I decided to actually do a little bit of research on geometric invariant theory. And that's what I'm going to present today, which is a general construction of how one should take a portion of a variety such that it is still a geometric object, which is a variety. Right, so let's start off with the basic definition. Wow, my it's not working. How do I skip page? Okay. So let us start off with the one of the main objects, which is an algebraic group, which is what we're gonna use to define an action on any variety. So an algebraic group is a variety, first of all, with that is also a group. And it has a multiplication map and inversion map, which are both regular morphisms. So in this whole presentation, we're gonna consider the left regular action, which satisfies these two conditions, which is normally seen, and the orbits. The orbits are using this notation and stabilizers and all. But I say that a G invariant morphism is a morphism such that it is constant on all orbits of any action of G. Right. So let's why is it that taking quotient of a variety so difficult? So what happens if you just take the set theoretic quotient? So normally if you take the set theoretic quotient, the orbit space does not really have a geometric structure, meaning it cannot be identified to be any variety at all. So for example, so if we let G to be the multiplication tool, and then we take the action to be defined like this. So the G times X, G times Y is a normal multiplication. So we see that all the orbits are the punctured lines that go through the origin. And at 0, 0 point, it is a fixed point. So we see that it is identified as a P1, but with the origin there. So you cannot say that it is an affine algebraic set or an positive algebraic set. You loses all the geometric structure. So you cannot just simply take a quotient or whatever. So to solve this problem, we introduce the so-called categorical quotient. So category quotient is actually a much more general definition. It works for any category. So let's read through the definition. Okay, so if we have a group acting on the object X, object X is from the category C, which you guys can see, and we call a duple Y and a pi, where Y is an object. First of all, it must be an object in the category, and pi is a G invariant morphism such that if you consider any other G invariant morphism from X to any other object in the category, it must search through pi. So what does this actually mean? It means that pi is the most optimal observer of the information in the orbit space such that it still preserves the geometric structure, or not geometric structure, but preserves the structure of whatever category that you are considering. So if we take, oh my god, if we are interested in the category of varieties, so then we must, a categorical quotient is then y must be a variety and phi must be a regular morphism with degree invariant. And one simple fact that you can see that since pi is a map from x to y, and you take the pullback, since pi is p-invariant, any image of the pullback of pi must be p-invariant too. So the image of pi star is entirely contained in the G-invariant, the ring of regular function that is p-invariant, right? So one important thing is that, okay, this will serve as a motivation as to how we construct the affine geometric invariant quotient. So from just now, the pullback is actually not just contained in the image of the G invariant regular function. It is actually isomorphic. To see this is pretty easy. So the surjectivity comes from the fact that the pullback, the way that we define pullback, totally agrees with how the universal property describes it. And injectivity comes directly from the subjectivity from right cancellation. Okay, that's an easy fact. So now we can think about it. If x is a variety and we have a categorical quotient, then we must have the ring of regular function of y isomorphic to linear, the G-invariant ring of regular function of x. And then if y were to be affine, then both of them must be finally generated. Because if y is affine, the ring of regular function on y is just the coordinate ring. Okay. So we now take ourselves to have another perspective, which is we take a look on this algebra rather than the geometric space, because it's very difficult to do that. So we define the expression on the functions, the regular function on any variety as such. Okay. So this is a very simple. I'm not gonna explain more. So next, we're gonna construct our affine GIT. But before that, we have to settle some scores with what kind of sufficient condition that I need to impose on algebraic group such that everything works perfectly. Okay, so if this is affine, as I say, the ring of regular function on x is the coordinate ring on x. Okay, so again we consider G and algebraic group, a general algebraic group on x, then we have this automatism. Okay, the following I will be introducing a lot of definition of what kind of algebraic groups. So let's start off with a linear algebraic group. Linear algebraic group, okay, I forgot to define linear algebraic group, but linear algebraic group is a closed subgroup of GL or GRN for some n. Okay, so a linear algebraic group is said to be geometrically reductive if there exists a invariant point and there exists an invariant homogeneous polynomial that is not constant, that does not equal 0. You can see that why this definition makes sense later. Like now it doesn't make sense, but it makes sense later. And then we have this marvelous super theorem, which is proven by Nagata. Okay, it says that if G is a geometrically reductive group, and when it acts rationally means if you consider, okay, if you consider any G invariant subspace, action of G on the G invariant subspace is literally linear action. Okay, it is totally describable by GRN. Okay, that's what it means. Oh my god. Then this theorem tells us that the subalgebra of invariant element is also finally generated. So we do not need to verify anymore whether or not SG is finally generated or not. Okay? So yes, as I said, there's a lot of definition. And we have a linear algebraic group that is linearly reductive if for every finite dimensional relation is completely reducible. meaning they can be decomposed into direct sums of irreducible representations. And okay, this proposition, I did not look at it a lot. Okay, I did not because it is a completely in the field of algebraic proofs. But yeah, it makes sense to put this proposition here just so that I can define the next definition. So a linear algebraic group is said to be reductive if its radical is isomorphic to the multiple of this multiplicative group for function. Then we know that in characteristic 0, one has a theorem from Well. I think people call it the Well unitary trait. You can use it to show that every reductive group is linearly reductive. And by the last proposition in this line, we have everything that we want. Okay, geometrically reductive implies linearly reductive. Okay, but when we are in a characteristic P, it's not 0 anymore. This might not work. But when Mumford is writing his book, he restricts himself to characteristic 0. But he believes that everything still works, even if it's not 0. Therefore, he conjectures that every reductive group is geometrically reductive. Okay? And then this conjecture is then proven by Habus. It is also written in the David Mumford book. He cited him. So now that we have everything is perfect, geometrically reductive is linearly reductive. Everything is perfect. Okay. So we should now try to construct our affine PID. So first, we let V to be a reductive group. From above argument, everything we just restrict ourselves to reductive group because when we restrict to reductive group, we can use Nagata's theorem and everything is finally generated and everything is stuff. Okay? If it acts on an affine group set, then there actually exists an affine group set such that the morphism satisfy the following condition. These 4 conditions, I call it the geometric properties. These 4 conditions must be satisfied for any kind of quotient that we are going to do in this one. Okay, I'm not going to prove this 4 because it's technical. It's a waste time. Okay, so I'm going to explain how do we construct things generally. So we construct the quotient of x, which is affine by derivative as follows. We just take a look at the G invariant coordinate ring. It is of course a subalgebra of x. You add up G invariant function is G invariant, you times a scalar is still G invariant, no problem. Okay? So by Nagata's theorem, we have this finally generated 3. Okay, so it being a subalgebra of AX, and AX is well known to be reduced, so AXG must be equal. Okay, and we construct our pi to be the corresponding morphism with respect to the K algebra homomorphism given by this inclusion map. Right, so AXG is just a G invariant function on X. Okay, it is still a function on X. Therefore, this inclusion makes sense. Okay? So I define the quotient Y. Y is to be so the quotient Y to be the affine variety corresponding to the finally generated reduced K algebra AFG. Okay. Then with Nalsadat, we know that every maximum ideal corresponds to a point. Therefore, we can have a complete explicit description of Y to be the spec of AFG. Okay. I know Yai here doesn't use spec as a maximum ideal, he uses prime ideal.
What? What's your question?
No. It's okay. Okay. So let's do an example. This example is the same example from the first one that we see that fails our test. Okay. So from previous, let me recall the G is a multiplicative group. And what is it again? Yeah, and the action is defined to be the times x by g, y by g, and then we define the action on the function as such. Okay. So from above, we know that if we try to find the quotient, we will find this coordinate ring, which is isomorphic to AXG. So we just have to find the set of all G invariant regular functions on X. So of course, the polynomial looks like this. Oh, I forgot to mention that X is A2, and that's why the ideal is bigger, so it's quotient by nothing is closed. So if we add G on it, you have this form, which G power I plus J. Note that G is not a group element, it is actually the ground field, the elements in the ground field. And so if this is invariant, then the coefficient fitness. Okay. Then this will give us two cases. One case where the power I plus J is zero. If it's zero, then x power I, y power j is all 1, all cosine. So we just leave with a constant. And if I plus j is greater than 0, then the above equation will tell us that Cij is 0. Therefore, we find that all the set of all invariant polynomials are just constant numbers. Okay? If it's a constant numbers, a coordinate ring isomorphic to the ground field, which is a field, therefore the ideal should be maximal. And this implies that y is just a single point. Okay. So we are done with the affine GIP. Now we go to when the case where X is a projective expression. So we know that the homogeneous coordinate ring of X is not the regular function on X. Okay? By Liouville's theorem, the set of all regular functions on X is just a constant number. So it's isomorphic to the ground field again. So we cannot use this to build our quotient because it is so trivial. Everything is trivial. You loses all the structure. So we cannot directly uses Nagata theorem here. So we try some other way. So what about we go the other way? Okay. So just now we define a quotient and then we show that it satisfies these 4 geometric properties. Now we go the other way. We say that the quotient is a good quotient whenever it satisfies all 4 geometric properties of it with an extra condition where pi is an affine morphism. Okay. So a good quotient is a geometric quotient whenever the quotient coincides with the orbit space. Meaning the set theoretic orbit space already works very well as a quotient. So of course we have these propositions. It tells us that good quotient and geometric quotient can be ruled out and can also be seen locally. It's like the shift. In fact, to prove this proposition, you need to use a lot of Dewey property of shift. Okay? Which I did not include the proof here, so go for the next one. So this is actually the showing that a good quotient is already a categorical quotient, which is what we want. To do this, if you want to show that a quotient is a categorical quotient, you have to show that all such invariant morphisms must factor through, okay, which is this first statement here. So how do we do it? So since D is any variety, and we know that for any variety, we can consider affine open cover for it. And then we can consider a UI, which is an open set of Y. Why is it an open set? It is given by the geometric properties where pi is a closed map. So this is a pi x take away this is a closed map. So this is UI is open since it is a complement. Okay? So then we show that UI actually covers the whole Y. We show it by showing that F actually maps the whole fiber in Y, whole fiber of a point in Y to a single point. Okay. And then we have to also build our unique morphism, of course. So this is a typo, I forgot to put a hat. So locally, of course, it is well defined because UI and VI is affine. From just now, we know that if it's affine, then everything works well. So this is a good regular morphism. Okay, that satisfy all the previous geometric properties and so on. So how do we form it? Is to consider the pullback. Okay, if you consider the pullback, we see that it's from AVI to this and to that, and therefore this corresponds this because VI is affine, it corresponds to another morphism which is FIV. Oh, I'm not wrong. So just now I'm wrong. This is not a typo. And then we again glue them again, and and we can form our unique homomorphism to actually those students. Okay. So if you want to talk about action on the positive variety, we also need to talk about how it acts on its affine code, right? So previously I say that what is irrational action? Irrational action is given by a linear action of GLM. But in the affine cone, if you donate by the scalar multiple in the GLM, it doesn't affect anything in your positive space because positive space is invariant under the scalar multiple. So we define it to be another morphism such that it sends every element in G to GL, and we want it. We want. Oh my god, hate this thing. Okay, we want it to agree with the projection of all the code embedding that we consider. Okay, so this is just a way that you define that you extend an action on a positive variety to its affine code. Okay, that both of them actually agrees with each other. So with this definition in mind, you then can consider its homogeneous coordinate ring, and since it is of course graded because of the degree of polynomials, so we can write it in this form. Okay, so let's have another example. This show that sometimes in positive space it doesn't work. Okay. So if we let our G to be the multiplicative group again, and we act on it like this, so this linearization is actually very obvious because they act in the same way in the positive and also the affine cone. Okay. Then we see that we have three orbits. One is the y-axis, one is the x-axis, if you look at it in A2, of course. And another, infinitely many ones are like a clock that turns from the bottom y-axis to the top, that avoids these two lines. So we know that its closure, of course, will contain these two y-axis and x-axis. And therefore, the 1, 0, and 0, 1, which is a perfectly closed orbit, are getting mapped to a same point in the quotient, which is bad because one of our geometric properties says that if the closure of the orbit does not intersect, it must not be a different point. Okay, this is bad. So this motivates us to actually to tell us that okay, maybe not every point in the projective variety is good for this action, so we throw away some of them. Okay, so throw away some of them, which is those unstable points, those that we cannot differentiate it using G invariant morphism from the origin of the affine cone. So if you follow Hilbert's notation, he called it the null cone. Okay, so if we go back the same example again, we see that if we throw away the thing the oh lord. Yeah, if we throw away one of the closed orbits, no, if we throw away one of the orbit, then everything works fine. The one key, if you throw it away, then you have a two closed orbit that maps to two different points, which is good. Okay. And we denote this as this, because so finally we are constructing the projective GIT. The construction of this is incredibly technical. So what do we do is that we uses the same idea as how we do it in the book photo. Okay. But in projective variety, let me think. Yeah, did I skip something here? Never mind, let me just talk about it. Okay. So there's a main problem in trying to glue up a bunch of affine open sets to form a projective variety. So you cannot just take any because their intersection sometimes might not be affine again. If it's not affine again, we don't know how to construct the categorical quotient locally. because we only know how to do it on affine case. Okay, so to solve this problem, we actually only consider distinguished open subset. So we see that if X, okay, I denote XF as a distinguished open subset of F, and XG the vice versa. So their intersection means that F and G cannot vanish at the same time. It is another distinguished open subset of F and G. And then it is again an affine variety and everything works well. Okay? And why is it that we see degree zero localizing here is that to work with the coordinate ring of a distinguished open subset, okay, distinguished open subset of a homogeneous degree greater than one polynomials in a projective variety. It is isomorphic to the coordinate ring of the affine cone localized at. Okay. So yeah, so we have to no choice, but we have to go into the algebra of this bunch of localized ring. We consider degree zero because we don't want the scaling to ruin everything. And so we're gonna follow the construction. We're gonna say how do we define the y-axis, and we're gonna glue them again. To glue them, we actually show that on in the overlap, if you see in the view of YF or in the view of YG, they are isomorphic. And so we can tell them how to actually glue themselves together and form a T variety. T variety is a variety that is locally affine. And then the T variety is an abstract variety. We don't know whether or not it is a positive variety or a variety. So we need to show that it is projective. And to show that it is projective, we have to use something that we call the Voronezh subgroup. Okay? It is very technical, so I'm not going to present here. Okay, so if we generalize it more, okay, following the idea of how do we linearize the action of a positive variety to an affine cone, we generalize it more. So now let X to be any variety. I don't want to just take the simple affine portion that only identify a bunch of closed properties. I want to introduce the notions of semi-stable and stable into any variety of important. So to do this, we kind of mimics what happened in projective varieties. So we take a line bundle and then we attach on it. So this line bundle, it is I don't think it's in my field, but we are doing it. So if you guys are interested, go and look at the details, please. No, just kidding. Okay, so a line bundle is a geometric object such that locally it looks just like a line. So for example, that I steal from India, Mobius link, the Mobius strip. So if you zoom it enough, it's just one line, one line, one line. But at one point, suddenly it turns 180, and then they glue them together. Okay. So if you attach the line bundle on a variety, so you can linearize the action on this variety up onto the line bundle. So how do we do that? We do that in this way. Okay, we just want it to satisfy some conditions such that it actually um agrees with the line bundle definitions and things like that. Okay. Yeah. And so now we don't talk about the regular functions anymore. We talk about sections. Okay. The sections, of course, the section is you can think about it as a vector field or something like that. It takes this point and gives you a scalar in the ruler or anything like that also can. Of course, it must satisfy that if you give me a point lying over X, if you project it down, it must give you the okay. And locally, if we are working with algebraic varieties, locally it must be a regular function. And then we have to define an action of an action on the section. That why do we define like this G and G inverse? Because we have to put it back and then push it forward again, just so that it is actually point in L lying over. Okay. And of course, and surprisingly, if you take a single line bundle, it's not enough because most of the time, if you take single line bundle, there are not enough global sectors at all. Okay. we are actually trying to build our function using the space of all these global sections. Just like how we do it by considering the, the bunch of regular function on our function. Okay. So this is one of the motivation why we take the R power tensor. But another motivation is that we wanted to create a greater algebra. Okay. So because we know that if you have LR1 and LR2, you cancel them together, then you get R1 plus R2. And we denote this set of global sections as this thing. And since we know that we just linearize the our action G on the line bundle, and we force it to be linear on the fiber. And this allows us to take the invariant setting. Okay. The set of all invariant section on this line bundle. And so one thing to note that is if F is invariant section of this R power tensor line bundle, then this set is actually open. But it is not necessarily open. Okay? It is open because locally it is indeed a polynomial. So if we define the zero locus of this function, on all the local patches, it is still the zero locus. And on the overlaps, since we are doing something in line bundle, so the transition function is given by a scalar. But it doesn't matter because z is when fx equals to 0. So the scalar doesn't exist. Therefore, z is a closed set in X. The set is a continuous, meaning that it is open. Okay? And then we have a new type of semi-stable definition, which is corresponding to the sections that we are talking about just now. So we say that point is semi-stable whenever there is an invariant section F of this R power tensor such that it is non-zero, and we strictly want it to be affine, the XF to be affine. It is not true that XF is always affine. Okay. And we say that it is stable whenever the set of stabilizer is finite, which is finite equal to 0. Okay, and the action acceptance. Okay. And at last, we have the most, obviously most, the generalized limitation on any variety when you consider line bundle and anything like that. So how do we do it is that, again, we take all such xfi because note that if a point is semi-stable, we can always find an invariant subject f evaluates on it is non-zero. So the set of all semi-stable is actually equal to the union of all such effects. Okay? Then we can find fi such that is, so we can find fi is suitable power such that it already covers the set of semi-stable stuff. Okay? This is actually what we have done in the Veronic subunit. It takes a lot of time to still present that. And locally again, because yi SFI is affine, if in the definition XFI is affine. And so we have a group quotient. We have a group quotient which is a yi and psi I. Then we can define, yeah. So again, it's equal to the construction in contributive variety. And then we show that we satisfy the full cycle condition. Then only we glue everything together. Okay. After we glue everything together, then we need to show that it's possible. Yes. So what I didn't mention just now is this cross operator. This cross operator is actually the set of all maximal homogeneous ideal that does not contain the irrelevant ideal. I did not present it because again it is very technical. Okay. Yeah. So following the same idea again, we can construct this and we can construct our morphism by doing all the morphisms. And that is all from me. Everyone stay good.
Okay, yeah, a couple of questions. Short ones because I think we're short on time. Can you go back one slide? What is H0 in that slide?
Oh, it's a space of invariant section from what called control line bundle.
And is it the zeroth cohomology or something?
That is a good question. I think this has a relation to the ample line bundle thing, which I did not. Yeah, which I did not go into.
Looks like
This is
the zero cohomology.
Yeah.
It's not.
So it's
I think
not
it
the zero
is.
cohomology.
Space of
Uh, uh,
global section.
Yeah, I'll leave you guys to talk about that. But yeah. The other thing is actually my other question is something that you also mentioned. I actually was going to ask you. Can you go back? I think one more slide.
Yes.
Yes. So you said L a line bundle. You do need it to be ample, right? It doesn't. You can't do this for like any line bundle. You need the positive degree condition. Yeah. Okay.
Yes. That is good.
Yeah, that's fine. This usually is part of the language. The other thing is the Voronezh subring. What is that?
Yes.
Can you remind me what that is? Actually, yeah.
Or the Voronezh subring is by you take common degree. You literally you make everything the multiple of a degree D. I
Okay,
kind of
so
forgot about
is
how do you get the degree D. Yeah.
it is a subring. So for fixed degree D. Okay, so it is a subring corresponding to the Voronezh embedding. Yes. That in
yes.
that. So yeah. Okay, never mind. And then the back to the slide you said like somehow. So that is just in some sense it is because for m positive degree, and then so if you're looking at it, yeah, actually, do you want to explain the somehow identical? Is that simply just because you're essentially straightening out your hypersurface into like some sort of like hyperplane?
When I was yes,
hyperplane divisor.
because
Yeah.
when I was proving for the positive case, and use of the fact that variances of the Voronezh subring is all of the same degree. So okay, I'm gonna be honest. The line bundle over X thing, it touches a lot of stuff in like control line bundle things like that. So I myself is also questioning myself when I was reading this. So I think it is somehow identical to what I have done using the Voronezh. Yeah, that's just why I put that.
Okay, I think I can sort of see that. Yeah, sort of replacing it with the hyperplane devices. Anyway, that's fine. Yeah. Okay. Yeah. That's no further questions to me. Thanks for the talk.
Right.
Okay.
Thank you very much, guys.
Thank you.
Bye.
Bye bye.